We did a problem similar to this way back a few weeks ago. We took, I think it was section 1.4. We took a ball and threw it upwards, and whatever the equation was, 70t minus 16t squared, we're going to call it. And what we did with that was we tried to look at the instantaneous velocity. And we did that instantaneous velocity using the average velocity, if you remember. The average velocity, we use that formula, distance equals rate times time, so velocity, rate, same thing. And so velocity being the rate, rate is distance divided by time, so the average velocity would be the distance traveled divided by the time, amount of time traveled. Well, the way we did it is, let's take, for the distance, start here at one height and then go a little bit of time to a new height. So, call that gap there the h seconds from this height to this height to be h seconds. And so what you'll have is, let's say this is time t here. So that's the height at t seconds. Then we go h seconds more, and we get a height of height at t plus h seconds. Okay, you with me there? So I start that. So that average velocity from here to here, you're going to take the heights, which the height of this one would be the height at t plus h. So it'd be s of t plus h. Minus the height at this one, which is at the t seconds, so that'd be s of t. And then we divide it by the times, time traveled, which is just the difference of the times, which, t plus h minus t if you want to. Of course, the t's are going to cancel. But do you remember what we did there? Then we took and we made it closer and closer together. We shortened the heights, said go from this height to then a smaller height and then a smaller height. Well, essentially what we're doing is we're letting h go to 0. And in so doing, what we find is this instantaneous velocity. We can spell it. At time t, not the average velocity, this is the actual velocity at time t. What we do is, we shrink our height here to 0. So we do the limit as h approaches 0 of these average velocities. Of course, the t is t minus t, so you just have the h there. Well, I say all that because what is this right here? Does that ring a bell? Does that look like anything familiar? Looks like the derivative, doesn't it? Yeah, that's the derivative of s. And so this instantaneous velocity, another application of the derivative is another application of the derivative. Instantaneous velocity is also the derivative. So there's our, if you count the tangent line as an application. But a velocity, given your height function or position function, it may not give you a height, it may just give you a position, if you think it that way, but yeah, that's also the derivative. Okay? All right, so let's go back here to this one. So now, we did that, the very first time we did this, we did it with a table. I don't think we didn't do any with limits, but now that we know what this is, it's the derivative, let's just utilize that fact. So let's A on this one. So let's find the velocity at t, for time t, for any time t. So again, this is our function. So what's the velocity going to be at time t for this particular function? Well, at time t, the velocity, that's going to be equal to the derivative. Which the derivative here, very easy, 70 minus 32t. So at any time t, give me that t value, and I can tell you what the velocity is at that particular point. And that's pretty nice, because all I'm given here is I'm given the height of the function, of the ball. And so I can figure out the height, but now, since I know the velocity is the derivative, I can figure out the velocity also. So let's find the velocity v. Find the velocity at 2 seconds and at 4 seconds. Find the velocity of this ball here at 2 seconds and at 4 seconds. Well, the velocity at 2 seconds would be the derivative evaluated at 2. And so we just take 70 minus 32 times 2, the derivative at 2. Whatever height it is, doesn't matter. That's going to give me my velocity. 70 minus 64. And that's 6. Now, one note here about this. I mean, you could probably guess what the units are, but if you go back and look here, the derivative is that, again, the definition of derivative, that's always important. If you look at what these are, the derivative is this. So the top one is the heights, and then the bottom here is the times. So the units are going to follow these, aren't they? It's the height units divided by the time units, which in this case the height units are feet, and then the time units are seconds. And I'll say more about that later on too, about some other stuff. But anyway, it'd be 6 feet per second. And then at 4, I mentioned that one because of what happens there. 70 minus 32 times 4 is 70 minus 128. Is that right? So it's negative 58 feet per second. Well, the reason it's negative is because there's a distance, there's a direction that's positive and a direction that's negative for velocity. And that's kind of the difference between velocity, just velocity, and speed. Speed is just, it's a positive, usually positive number. Velocity is directed, and so we've got a positive direction for velocity, and then there's a negative direction, the opposite direction. And so that's what this is kind of verifying out. This one's at 2 seconds is still on the way up, but at some point it turns back around, whatever it is, and it comes back down. And so that's what this is saying. It's the opposite direction as that 2 second velocity, because it's traveling an opposite direction. So velocity is just directed speed. There's a direction. Anyway, the other one here, they might throw at us. I know this one gets a little tricky, so let me do that one. All right. So find the velocity. When the object is at Five feet. No, that one should work. Find the velocity when the object is 5 feet. Well, so what this entails is, yeah, I still want to find the velocity, but I don't know what the time is for that particular velocity, do I? It gives me the height, and so for that particular problem, we'll just have to figure out the time. I think there's actually going to be 2 times here that this is going to work. Because this gives me the height, and so to find out this velocity, I have to figure out the time, because that's what the velocity depends on. It's the time, not the height, or I need the time to figure out the velocity. So if I've got a height of 5 feet, I have to go back to this equation. I know the height is 5 feet, so let's go back to the height equation in this particular case. So it's S equals 70t minus 16t squared. The height being S, so I'm plugging in the 5 here for my S, which sets up a nice little quadratic equation. One side need to make it 0, so let's make it 16t squared minus 70t plus 5. That equals 0. And then use the quadratic formula, because I don't believe that one's going to factor. T equals negative b, so it'd be 70 plus or minus square root of b squared, negative 70 squared, minus 4ac, so it's minus 4 times 16 times 5. Divide that by 2a, so it'd be 32. Use the quadratic formula there. All right, so let's see what we get. It gives me 70 plus or minus square root of, that'd be 4,900. And that would be minus 4 times 5. We go into the square root here, we got 4,580. So we got 70 plus or minus, give or take, 4,580. Let's call it 67.7. Divide that by 32. And so that's going to give you 2 times, so 70 plus 67.7. Divide that by 32. So it's either 137.7 divided by 32, or 70 minus 67.7. Divide that by 32. It's a point. 2.3 divided by 32. That's going to be a small number. This is about 0.07. And then this one on top is 4.30. So yeah, it's gonna reach that height, 5 feet. Like I said, it's going up and coming back down, so it hits that 5 feet in two different places. One real quick at 0.07, or I guess it's gonna round it off to 0.1, but so find the velocity of the object at 5 feet. Well, on the way up, the velocity at 5 feet well, it's going to be 70 minus 32 times 0.07, right? Whatever that is, that's going to be 67.76 feet per second, same as the other. And then the velocity at 5 feet on the way down, well, it'll be 70 minus the other 32 times the other time, whatever that is. Negative 67.7. Yeah, that makes sense. Should probably be the same, but my rounding kind of messed up a little bit. Even the same, but yeah. Anyway, interesting little problem. Is that okay? Any question? Is that okay? So, velocity is another application of the derivative. Now, we can expand this, though, even more because, like we said, velocity, we can think of it as a rate. Velocity is a rate of change. It's the rate of change of a height function or position function. I mean, we could do, we did the one here that it was the height, but sometimes they'll say your function represents a position. It's at this position at time t, and then so forth and so on. Well, velocity is the derivative of all that, okay? So, both of those then say the same thing, okay? Well, what I'm getting at here is, since velocity is rate of change, this derivative, the derivative can be thought of in terms of any, if you've got any type of function, if you do the derivative of it, what that gives you is this rate of change of that particular function. So the derivative not only can it be applied to this velocity setup, but you can do any kind of function and do the derivative, and it's going to be what's called the rate of change. The rate of change of your function, whatever it defines, okay? So the derivative of any function, whatever it describes, one application, or the application of that, is that the derivative describes then the rate of change for that particular function. All right, I'll give you a couple of examples here. Yeah, so here's not really an application, but more details, okay? So if I've got y equals f of x, what does f prime represent? This is kind of a question they will ask us several points along the way. What does the derivative represent for that? What does f prime represent? Well, what they're getting at here, what they intend for you to understand, is that the derivative represents a rate of change for this particular function. So f prime is the rate of change of f. And sometimes there's kind of multiple things going on. So if we're doing y equals f of x, it's the rate of change of f with respect to our variable here, x. And so that's kind of the phrasing that they like. It's the rate of change of f with respect to x. Now, if I change it, and well, let me mention this before moving on here. We got to it a little bit on these this velocity. What about the units of f prime? Yeah, because in applications that becomes more of an issue, more of a thing. What about the units of f prime? Well, again, going back to the very definition of the derivative, f prime of x is the limit h approaches 0, f of x plus h minus f of x over h. Well, if you look at, so the units of f prime would be the same units as I have here. Well, the top units, that's units of f. So the f prime units would be, the units of f would be the top. And then on the bottom we've got h, but remember back what h is dealing with? H is that change in the x. So the h units here, those are the units of x, whatever the x is here. And so whatever your function is, the derivative units will be the units of the function you start with divided by the units of whatever the x is. And it could very well not be x, but all right. So let's talk about a couple of examples here. I mean, this is pretty general. Let's see some specific ones. Maybe that'll help. Okay. All right. Suppose if the number of bacteria in a culture after T hours is given by y equals some function of t, let's call it b of t. Not really specifying what it is, okay, it's just some function of t. Y equals some function of t. All right, so A, what does y prime represent? Well, y prime's the derivative, and so we were just talking about that. The derivative represents a rate of change, so any derivative we have, that's what it represents, a rate of change. And so in this specific case, y prime would be the rate of change of what? Well, in this particular case, the function represents the number of bacteria, right? So, y prime is the rate of change of the number of bacteria with respect to the number of hours, T hours. So again, that's kind of the phrasing we like here. Y prime in this case represents the rate of change for the number of bacteria with respect to T hours. Okay? Right? What about the units? What are the units of y prime? Again, the units of the derivative are always the units of your function. In this case, the units of y divided by the units of your variable input value, whatever you want to call it, which in this case is t. So y is the number of bacteria, so number of bacteria. Y is the number of bacteria, bacteria. And then in this case, t is hours, so bacteria per hour would be the units. Sort of makes sense? It's always, what does the derivative represent? It's the rate of change of whatever the function is. And then the units is always, that's the way it always sets up. So they'll ask several questions like that. Here's another one. If, suppose, C equals, and I'll put some numbers, all right, C equals negative 10,000 plus 200x minus x squared. That represents the cost to produce x units of a certain item. C represents, C, the cost to produce x units of an item. All right, so let's go through the same two, and I'll add another one because they'll ask it a little differently sometimes too. All right, so A, what does C prime represent here? Well, what I'm trying to hammer home here is the derivative represents a rate of change. And so in this case, C prime is the rate of change of, our function is the cost function, so it would be the rate of change of the cost with respect to the number of x units produced. Okay? So like I said, it's pretty much the same verbiage, just have to change what the function represents. C prime is the rate of change of the cost in this case. So it's always, derivative is always rate of change. In this case, it's the rate of change of the cost with respect to the x, to x units produced. All right. What are the units of C prime in this particular case? Well, since we're here in the United States, I didn't tell you, but I would suspect those that cost is coming out in dollars. I guess it could have been cents, so I match in dollars, US dollars. And so the units of C prime will be the units of C divided by the units of x in this case, be the units of my derivative. So again, talking about dollars, units of x, well, it's x units produced. Like that. So, dollars per units produced. All right, now here, is that okay? Okay. C on this one. What does C C prime of 50 equals 100 mean? What does C prime of 50 equal 100 mean? What is it that we found here? We got C prime of 50 is 100, but what does that mean? Well, you just have to kind of figure out label-wise what these parts are. Of course, this is the value of C prime that we have here. What's the 50? 50 would be the X, right? Which in this case, X is the units produced. Well, I haven't found here the cost of my units produced. That's not the cost of units produced. What does this 100 represent? It's a rate of change. So what this is saying is C prime is 100, and so that's the rate of change. So the rate of change is $100 per unit when the X is 50, which is, in this case, what does the 50 represent? Units produced, when 50 units are produced. So again, same verbiage, different application, different type of problem, but yeah, just FYI too, if your business, going into the business world there, this, if you've got a cost function, do the derivative, it's also called the marginal cost. But you don't have to know that for these particular problems. Anyway, got one other one. Finish up on. Going back to the velocity and the position function. All right, so let's say we were able to come up with a position function, and let's don't call it a height, let's just call it position. Say our position at time t was s. So we've got an s of t. Equals our position at time t. Similar to what we did with the height function, but it is just a position. It may be, right and left instead of up and down, or some other directions. But anyway, that's our position. Give me a time and this function, plug it in. That'll give you the position you're in. All right, so if I do take my derivative of s, what does that give me then? Well, the derivative of position, that's velocity. Okay. All right, and so that's going to give me, the derivative gives me the velocity at time t. Well, think about this. So let's say I'm cruising along at a certain velocity, but in this position function, maybe there's a point, at some point, it takes off and goes quicker. Well, all right, so got the velocity is the same, then it gets, all of a sudden gets quicker. What did I do when I got quicker? Well, like we say we accelerated. Well, what happened there? Well, the velocity is this rate of change of position. Well, what happens if I change my velocity? I've accelerated, haven't I? Or if I'm going along and I start going slower, I decelerate. But what I'm getting at here is that if I do the rate of change of my velocity, that's acceleration, isn't it? Because, like I said, if I'm going along and then I change my velocity changes, that's acceleration, whether it's increasing or decreasing. But all right, so the point of all that is that if I do the derivative of the velocity, which if I do the derivative of the derivative, that gives me the second derivative. Here's an application of the second derivative. The second derivative is of the position is the acceleration at time t. So an application of the second derivative is, I'd say, well, why even do a second derivative? Well, in this particular model, acceleration is found by doing the second derivative. We started with the position, take the derivative that gives the velocity. The second derivative gives us then the acceleration at time t. Okay, so let's say a particle moves in a straight line its position at time t is s equal t cubed minus 8t squared plus 15t plus 10, where t is in seconds and s is